Hi, this is our second look at the kinematic formulas, but now we're moving from the more basic formulas into some of the more intricate, a little bit more advanced formulas. What we're going to see here is formulas that are going to combine some of the definitions that we have or some of these other kinematic formulas to get us a one-stop shop for one formula to use if we want to solve for something specific as opposed to having to take multiple steps. So what you're going to notice is each slide here will tell you what you're solving for and what you don't know, right? That becomes an important piece. If you recall from one of the previous videos, we tell you write out every single one of the variables, and then hey, if you don't know acceleration or you don't know time or you don't know final velocity, it's going to tell you, hey, if you don't know that, this becomes a good formula to use. So our first one that we have here, right, to solve for displacement, if we look at our two ways that we can have average velocity, so delta x over delta t and initial plus final velocity divided by 2, right? Each one of those work when we're under a uniform acceleration. So we can set those two formulas equal to each other, right? Where we have delta x over delta t is equivalent to vi plus vf divided by 2. So when we rearrange this, all that we've done to get that formula in red is we've multiplied delta t from the left side over to the right side, and we've pulled that fraction out. So instead of being divided by 2, we just multiply it by 1/2. So that formula in red states is our displacement is equal to 1/2 times the sum of the initial plus the final velocity times the time interval, right? We do that, we're going to be able to directly find displacement. Now, this formula also works if we don't know acceleration, but we know, let's say, 3 of the 4 variables listed here, and we wanted to find the 4th one. It still works. So remember, we can rearrange these formulas to get what we need. But again, all we did here, average velocity, rewrote it in terms of displacement, and here we don't know the acceleration, but we have other information that we can go off of. So for our next formula out of our kinematics, here we're going to rearrange to solve directly for the final velocity. And this would be a case when we don't know what our displacement is, right? So we can find velocities using accelerations and times without that displacement. All that we did here is we took the definition of our average acceleration, which is delta v over delta t. We broke apart the delta v into its components. So we actually write out the final minus initial velocity. And then from here, it's an algebraic rewrite to get the final velocity by itself. So multiplying time from the right to the left, and then adding the initial velocity over, right? That's where we get our final velocity is equivalent to our initial velocity plus the acceleration times the time. Note again, if we don't know displacement, this becomes a good place to go. If we don't know it and if we don't want to solve for it, this becomes a good formula to choose. We can rearrange this to solve for any of the 4 variables that are present as well, but we'll write this in terms of final velocity. This next kinematic formula, again, we're going to go back to solving for displacement, but now if we don't know what our final velocity is, right? So let's say we look at this and we go, boy, okay, I know how fast I'm going at the start. I know what I'm accelerating at. I know my time. I just don't know how fast I'm going at the end, but I want to know how far I've gone, right? What's my displacement? So we can take the formula from the previous slide, rewritten, right? VF equals VI plus A delta T. Again, just our definition of average acceleration rewritten in terms of final velocity. And then we can take our displacement that we have from one of the previous slides as well. By substituting the final velocity on the left into the formula on the right, that allows us to combine these two formulas and get what you see in red, which is that our displacement delta x equals our initial velocity times the time interval plus 1/2 times the acceleration times the square of our time interval. Again, where that comes from is our substitution. So we take vi plus a delta t, sub that in for v of f on the right-hand side. You can work out the math, and we can see that this is the formula that we are left with. So again, this is a great one-stop shop to finding displacement without needing to know final velocity. Otherwise, and you certainly could do this, you could use the formula in the top left here to find v of f, and then plug that into the formula on the middle there, in the top right, to find delta x. This again provides you one location that you can go. You've probably noticed that for the previous formulas, we always had time, right? Time was always, always, always there. But if we don't have it, right, that then becomes difficult. Like, what if we don't have time? Time is a very, very important thing in physics. Critical, crucial, very important. We're not always going to have it though, nor will your time intervals, especially if you're measuring something, necessarily be as accurate as you would hope them to be. So if we don't have time, we can take a handful of those previous ones, substitute in, right, perform a whole bunch of derivations, and we can get this expression here, where the square of the final velocity is equal to the square of the initial velocity plus 2 times the acceleration times the displacement. So again, to reiterate that, the square of the final velocity is equal to the square of the initial velocity plus 2 times the acceleration times the displacement. Now, one thing that's great about this, right, and something to notice, and it really ties in some of our definitions here. What happens if the displacement is 0? Well, if the displacement is 0, that means delta x is 0. That means our initial and our final velocities, right, that's going to tell us if we didn't go anywhere, right, if our displacement is 0. So that means they're either opposite directions or they're both 0. If our acceleration is 0, that's going to tell us that our final velocity will match our initial velocity, right? It works out really, really nicely there. And again, something to keep in mind, if we don't have time, we can solve for any of the 4 variables that are present here. So we can use this to solve for final or initial velocity, acceleration, or displacement. So overall, right, as we look at our one-dimensional formulas here, just holistically, all the formulas that we've looked at over the last 2 video lessons, we have our definitions, which work all the time. No matter what, you can always fall back on these, provided you have enough information. Right, so we can look at our average velocity and our average acceleration. Again, note the words average in there. Your average velocity is not always going to be your final. It's not always going to be your initial velocity. Your average velocity will be your initial and your final if there is no acceleration. So we get our definitions here. Then we get the other 5 expressions, right, that were recently introduced here, right? 4 of them in particular, right, are being introduced. These are only good when the acceleration is uniform, right? When it's constant, which is only what we're going to look at anyways. So on the left-hand side, you're going to see the formula. On the right-hand side, you're going to see when these are best to be used based on what variable you do not know. So the new formula is there on the left. When to use them is going to be on the right-hand side. So notice that each one of those formulas in the bottom 4 there, they're all missing one piece because there's 5 primary variables that we work with: our displacement, our initial and final velocity, our acceleration, and our time. So we have 5 primaries, and out of those primaries, one of them is going to be missing in each one of the formulas. This gives you a nice place to look instead of digging through to find formulas. Here's a table of them, right? Use them as you see fit and get some good practice with them. Now, these formulas can be applied to the graphs as well. They don't have to be. At this point, we conclude looking at the math and looking at how we can govern one-dimensional kinematics using the mathematical expressions that are present here.